Hello students, welcome to the amazing platform of Physics Wala. Welcome to the PW English channel, my dear students. Today we are on the lecture 3 of solid state. Till now we have discussed a lot of important things. We have discussed about the different types of solids, a theoretical part of solid state, my dear students, classification of solids, and I must tell you generally questions are asked from this theoretical part, so you need to read this particular part from the NCERT as well. Okay, so what are we going to discuss today? We have discussed yet till now we have discussed about what is a lattice. We have also seen a different types of lattices, one dimensional lattice, two dimensional lattice, and three dimensional lattice as well. Then we have also discussed about the different arrangements that are possible, right? Yes, so now my dear students, we will be discussing about the rank. What is rank? You will just get to know. We'll also discuss about coordination number. You will also know what that actually means. These are the few terms which will be used in the whole chapter forward. Okay, I hope all of you are excited. Ma'am is super excited. Let's start the amazing session today. So let's talk about the crystal system. So before discussing about the arrangement, I just want to tell you that, my dear students, we'll be discussing only and only the cubic crystal system. This is the only crystal system in our syllabus. Other than this crystal system, we are not going to cover anything else. Okay, so cubic crystal system is something which we will be discussing today. Okay, let's talk further, my dear students. Not only today, in fact, in this full chapter, we'll be discussing only cubic crystal system. So don't consider any other crystal system. We'll be discussing only cubic crystal system. Whatever rules I'll be telling you, all those will be applicable only to cubic crystal system. Okay, yeah. Now let's start. So the first point says that constituent particles are considered to be solid spheres. Their shape can't be deformed by the application of stress. They may or may not make contact with each other, but they never merge into one another. So now, my dear students, I just want to tell you that whenever you will be considering the packing of a crystal system, what few things you need to memorize or you need to understand, you need to keep in your mind, and those are, my dear students, let's say we have a unit system, something like this. You have a crystal system, unit crystal system. Okay, and so now what happens here is, my dear students, that you know that atoms are arranged. Let's say atoms are arranged on the corners. So what are the different possibilities that the atoms can be arranged? Okay, so the first assumption that is made is that these atoms are solid spheres. They are pure solid spheres. They are not spongy. Okay, you cannot compress them. They are solid and hard. Okay, so now what actually happens is, let's say we consider a edge, this, and we consider atoms over it. Let's say I said atom is here and atom is here. Let's say the radius is r and the radius is r, and let's say the edge length is a. Okay, yeah. So the first possibility is that this a is, let's say that this a is actually more than 2r. That is the sum of the radius, and there is some x amount as well. Okay, so it is a possibility. This is possible. Okay, your edge length might be more than the sum of the radius of these two. Okay, what is the other possibility? This is possible, so I'll say this is possible. Okay, let's talk about the other possibility. Let's say you have a edge length like this, and you have two atoms like this and this. This is r, and let's say this is a. So I can say that a can also be equal to 2r. The edge length can be equal to the sum of the radius of the two atoms. This is also possible. What is the other condition? The other condition might be that, ma'am, you might have a edge here, and you have a atom like this, and you have another atom like this. So this is r of this particular part, and this is r of this particular part. Okay, yeah. So what does this mean? This means that your edge length is less than 2r. So, my dear students, this condition is not possible. No, you cannot consider this as a factor in the packing. Okay, your solids are spheres, your atoms are solid spheres, so they cannot merge into one another. Yes, they can be far apart, they can exactly touch each other, but they cannot merge into one another. This condition is never possible. Okay, I hope you're clear with this particular part. Okay. Yes, this is something you have been told in this particular part. Okay. Yes, you cannot compress the atoms. You cannot compress the atoms. You cannot stretch those atoms. The atoms are solid and they have a fixed volume. Okay. Yeah. I hope this is clear to you. Next is lattice points are located at the center of the sphere. Now, what does this mean? This means that let's say you have a edge length here, then the atom will always be present at this particular part is its center. So the lattice point, which point we consider, will always be considered at the center of your sphere, at the center of your sphere. Okay, I hope you're clear with this. So pause the video, write this down. These are the few things which you need to keep in your mind. You can draw this as well. Okay. So now, my dear students, we have discussed about the different types of arrangements, and I told you that we'll be discussing the different types of arrangements in only and only cubic crystal system. Okay. So now in cubic crystal system, we are considering the different types of arrangements. I just want to know that how much of the effective atom is present in one particular crystal system. I'll just make you explain what I said. Okay. Just a second. Let me just see the temperature. Yeah. Okay. Okay. Now, my dear students, let's think about a word which is rank. What does rank mean? Rank means that how much effective atom is present. How much effective atom is present. Now, what do I want to say by that? Okay, now to make you understand this particular part, let's us consider that I ordered a pizza. I ordered a pizza. Everyone likes pizza. I know you like pizza. Okay. So now the pizza is something like this. It has parts like these. It has 6 parts. 1, 2. So, awful drawing. This, then this, then this. Okay. Your pizza is something like this. Okay. So now, my dear students, what happens? I just take one part of it. I take one part of it out. Okay. Yeah. So can I ask you that how much of the pizza have I ate? I have eaten one. This was 1, 2, 3, 4, 5 and 6. So ma'am, you have eaten 1/6 part of your pizza. Okay. So now what happened? All of you all were my friends, so I gave all of you also the pizza pieces. Okay. So now every friend has 1/6 of the part. My every friend has 1/6 of the part of the pizza. What if I bring all the 1/6 together? What will I get? I'll get the sum equal to 1. 1/6 into 6 will give me 1, right? Yes. So now, my dear students, we can see that there are different parts and the sum of all the parts will give you 1. Okay. Yeah. So from here, you'll understand the rank. You put an atom over the unit cell, and now we are considering the cubic crystal system. You add an atom on the corner. Can I ask you that how much of the effective atom is actually present in the crystal system? That is what is known as rank. The rank is the effective number of atoms present per unit cell. How many effective amount of atom is present in the unit cell? Okay, you will get a better understanding when we'll discuss the crystal system. For the time being, you can just write it. I hope you've written it. Okay. Now let's consider the rank. Okay. So now, my dear students, just ignore what is written here. You just need to understand what I want to say. Let's consider a cubic crystal system, and let us consider that I have added atoms at the corners. Okay. So the atom would be here at the corner. I hope you're clear with this. The atom is present here. Now you'll understand this in a very interesting way. Okay. I'll just draw a diagram and then you'll understand. Okay. Okay. So this is my unit cell. Now, okay. So this is my unit cell. Okay. So you can consider this as a room. Now, imagine, my dear students, you have put a ball. Atom is a sphere, so we can consider it as a ball at the corner. Okay, so now if your ball is present at the corner, how much part of it is effectively inside the unit cell, that you have to find out. Okay, so if I consider this as my room, can I say that this is my ball? This is my ball present? Yes, ma'am. Now let's try to find out how many atoms are present. Okay, see, here also adjoining this particular room, you have another room. This is the room. You have a room with just next to it. Yes, you have a room. So this is the part, this is the other room. Now imagine you have these two rooms. Obviously these two rooms backward also you have two rooms. So you have two rooms backward as well. I hope you're getting it, right? Yes. So can I say that this one atom is divided into 4 rooms? This one atom is at the corners of 4 different rooms. One room, the next room, the room behind, and the room behind the next room, right? Yeah, the 4 rooms, you have this. So can I say that the contribution is 1/4? Okay, fine. Till now, you're clear. Now imagine since it is a lattice point and 3-dimensional lattice point, my dear students, there will be some room above this particular unit cell as well. Will there be a room here? Yes, there will be a room above this room as well, and this corner atom will be in its corner as well. Similarly, there will be a room adjoining this as well. Yes or no? Yes. So this will be shared in that as well. Okay, this room, this room. Also the 2 rooms behind will have 2 rooms above them. So I can say that this one particular atom, this one particular atom is actually divided in 8 different rooms. This one particular atom at corner is actually divided in 8 different rooms, and in each room the contribution now will be 1/8. 1/8. So the contribution of an atom at the corner is always equal to 1/8. Okay, I hope you're clear with this. So you can write here that contribution at corner, let's say NC, is 1/8. It is always 1/8. One atom at the corner means you have 1/8 of the contribution. See, okay. So if I say that I have a room and I have atoms present at 2 corners, the contribution at one point is 1/8. The contribution at one corner is 1/8, right? Yes, I have atoms present in 2 corners. So can I say the total contribution is 2 into 1/8? That is 1/4. This 1/4 is the effective amount of atom which is actually present in the unit cell. This is the amount of atom present in this one room, not in all the rooms. In this one room, how much it is present? Only 1/4. This is known as rank. This is known as rank. Okay. So the contribution for corner is 1/8. Okay. The contribution is 1/8. Let us say NC is the number of atoms at corner. So the total contribution would be number of atoms into 1/8, right? Yes. So now we'll derive a formula here, my dear students, that at one corner the contribution is 1/8. Let us say we have n number of corners. So how much will be the contribution? Number of corners into 1/8. And rank is actually the effective number of atoms. So this would be NC/8. Okay. What is NC here? NC is the number of atoms at corner. And contribution of atom at one corner is equal to 1/8. Okay, so this is something we have derived till now. Now you'll read the line and you'll understand. The corner atom is shared by 8 cubes. 8 cubes, 4 these and 4 above. Okay, therefore its contribution to 1 cube is 1 by 8. Perfect. I hope you're clear. Now let's move forward. Please write it down. If you want to draw this diagram as well, you can draw. You can just draw it like this. It will be a little more clearer to you. That here also you have a set of room. Okay. Okay. I hope it is clear. Let's move forward. Now let's talk about the unit cell. Now let's consider a atom is present at the face center. What is the face center? Let's say this room and this wall is a face, and let's say the atom is present at the center. Okay. So if your atom is present at the center, if your atom is present at the face center, my dear students, if your atom is present at the face center, then it is being shared in how many cubes? This room, this face, and the other room, right? Yes, only these two are sharing one atom at a face, because this wall is shared between only 2 cubes, 2 rooms. So can I say that one more room would be present here and it will be shared only in these two? So the contribution would be 1 by 2. So can I say that contribution of one atom at face center is 1 by 2, and let's say NF is the number of atoms present on faces. So the rank would be number of atoms present on face, that is NF into 1 by 2. So this is NF by 2. So this is NF by 2. Okay. Yes. This is for face centers. Okay. Let's say this is our second equation. Let's say this was our first equation. Okay. We'll use these, don't worry. Now you can read this. The face atoms are shared by 2 unit cells. Therefore, its contribution to 1 cube is 1 by 2. Okay. You can write this down. I hope you've written it. Now let's move forward. The next is for body center. Now imagine you have an atom and that is present in this room in the center. Here at this particular point, it is just roaming around or it is just standing in the center. Then is it being shared in any other unit cell? No, it is not being shared in any other unit cell, because this time the atom is present here. It is not being shared by any other atom. Then the contribution would be complete 1. Yes. So contribution of an atom at body center is equal to 1. Let's say NB is the number of atoms present at body center. Okay, so the rank would be NB into 1. So the rank will be NB, right? Let's say this is your third equation. Let's say this is your third equation. It says the atoms inside the cube are called body atoms and they contribute their whole to the unit cell. Okay, yes, I hope you're clear. Please write it down and then we'll move forward. Okay, I hope you've written it. Now let's move forward. Next is the atoms are present on the edges. Now, my dear students, what if your atom is present at one of the edge? What is edge? This line is actually the edge. Okay, so what if, my dear students, your atom is present here? Now you have to imagine that in how many unit cells is this being shared. Okay, so you'll have to imagine a edge. Now consider an atom present here. In how many rooms is it being shared? You'll say that, ma'am, it is being shared in the adjacent room. It is being shared in the adjacent room. Ma'am, there will be a room behind as well. There will be a room behind as well, right? Yes. And ma'am, there will be a room behind this as well, right? Yeah. So this particular room, this particular atom is being shared between 4 different unit cells or 4 different rooms, right? Yes. So can I say that contribution of an atom at edge is 1/4? Let's say Ne is the number of atoms present at edge. Number of atoms present at edge. So the rank will be equal to Ne into 1/4. So the rank will be Ne/4. Let's call it our fourth equation. Let's call it our fourth equation. Okay, I hope you're clear with this. Perfect, my dear students. You can pause the video and write it and draw it as well. I hope you've written it, right? Yes. Now, my dear students, you can have a unit cell where the atoms are present at the corners, at the body center, at the face center as well. You don't know wherever atoms are present. So we can find a generalized formula. So generalized formula for rank is given as rank is equal to number of corner atoms by 8 plus number of face center atoms by 2 plus number of body center atoms plus number of end center atoms by 4. So this is the generalized formula that you can use for calculating the rank of any unit cell. Right? Yes. So this is the formula we'll be using again and again. This is E. Okay? Perfect. You can write it down and then we'll move forward. Okay. I hope you've written it. Now let's try and solve a few questions and we'll have a better understanding of this rank. Okay. So let's say I gave you a question and my question is calculate the rank of a let's calculate ranks for each and every unit system now. Yes, let's write the heading as rank in primitive unit cell. So if you have a primitive unit cell, my dear students, if you have a primitive unit cell, then what will be the total rank? Okay, so I can say that for a primitive unit cell, atoms are present at the corners, right? Yes, so atom would be here, as well as here, right? Yes, so I need to calculate the rank and I know the formula for rank, that is number of atoms at the corner into 1/8. How many corner atoms are there? 1, 2, 3, 4, 5, 6, 7, 8. So ma'am, 8. Contribution is 1/8. Do we have any atom at face centers? No. Do we have any atom at body center? No. Do we have any atom at edge? No. So all else would be 0. So can I say that the rank of a unit cell is always equal to 1? So the rank for a primitive unit cell is always equal to 1 because the atoms all are present at the corners only. Okay, perfect. So this is how you calculate the rank of a primitive unit cell. Okay, I hope you're clear with this. Now you have to find out the rank for a body centered unit cell. Rank for body centered unit cell. So if you have to calculate the rank for body centered unit cell, my dear students, so you need to draw a body centered unit cell. Okay, so you have a unit cell. Let's join these. Now in a body centered unit cell, your atoms are present at the corners, also at the center of the body, right? Yes. So now let's try to calculate its rank. What will be its rank? You have corner atoms 8, so 8 by 8 plus you have body centered atom 1, so 1 into 1 plus, else you don't have any other thing, so total your rank would come out to be 1 plus 1, so rank is equal to 2. So always and always the rank of a body centered unit cell will come out to be 2. The rank of a body centered unit cell will come out to be 2. Clear? Yes, perfect. Please write it down. I hope you've written it. Now let's move forward. Let's calculate the rank for face centered unit cell. Okay. So if you calculate the rank for a face-centered unit cell, you'll need to draw the face-centered unit cell. So let's try to draw the face-centered unit cell. Okay. In face center, you know that atoms are present at the corners. Also, they are present at the face centers, all the face centers. Yes? Yes. All the face centers. Okay. So now we have to calculate the rank. So for rank, again, my dear students, you have NC by 8 plus NF by 2 plus NB plus NE by 4. Okay. So number of atoms at corners are 8. So 8 by 8 plus number of face center atoms 1, 2, 3, 4, 5 and 6. So total 6 are present, so 6 by 2. So this would be 1 plus 3, which is equal to 4. So the rank that came out for a face-centered unit cell is equal to 4. So how much is the rank for a face-centered unit cell? It is 4. 4 effective atoms are present in a unit cell. This is how you calculate the rank for a face-centered unit cell. Please write it down and then we'll move forward. Now, you will get a homework. You have to calculate rank for end-centered. Though in world, this end-centered doesn't exist. But again, for your learning, I want to give you this cubic end-centered unit cell. Let me say unit cell. This is cubic, okay? So this is your homework. You have to try and calculate the rank for a end-centered cubic unit crystal system. Okay, yes. Try this. I know you'll do it. I have told you what is the arrangement. Just make the arrangement and calculate the rank using the formula. Okay. I hope it's clear. Let's move forward, my dear students. Now, Now, the next important thing that we need to understand is the characteristics of a cube. So now, my dear students, you need to be clear with the characteristics of a cube. What is a cube? What different properties you need to understand about cube, because questions will be asked from this particular part. So my dear students, let's try and understand everything. Okay, so if I ask you how many total corners are present in a cube, you will say total corners are 8. No issues. Can I ask you total number of faces? Let me say number of corners. The other thing is number of faces. How many number of faces are present? You have 6 different faces in a cube. So you have 6 different faces in a cube. Okay, let's talk about the other thing. Let me ask you, how many number of edges do you have? Number of edges. What is edge? I told you this is what is known as edge. Okay, so how many edges are present? You have 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11 and 12. So the total number of edges that are present are 12. So you need to know what are edges, what are faces, how many face centers and everything, because you will be asked questions based on this. Okay. Yes. Now, you know the number of corners, you know the number of faces, you know the number of edges. If I ask you number of body centers, ma'am, body center is always 1. So the body center is 1. This is your body center. Okay. Till now, everything is clear. If I ask you, can you tell me how many edge diagonals are present? How many number of edge diagonals? Now, this is something important because you need to know this. Now see, my dear students, this is a face. Okay, this particular part is edge. Okay, this is a corner. This is a corner. Till now, everything was beautifully done. Nothing was very tricky. This is the body center. Okay, I'll make you draw body center at the end. I just want to show you something also. Okay. Okay. Now the question is edge center. Sorry, edge diagonal. What is edge diagonal? So my dear students, you know that this is your edge. You also know that this is edge. So the edge diagonals are always completely a diagonal drawn from one edge to the opposite edge. Completely opposite edge. Okay. So this is a edge diagonal. This is a edge diagonal. So I want to ask you that how many total number of edge diagonals are present? You know that you have 12 edges and 2 edges together combine and give you one diagonal, right? So how many edges can be present? If you have 12 edges and 2 give you one edge diagonal, then you have 6 edge diagonals. So you have 6 edge diagonals. This is something which you need to understand. Okay. So you have 6 edge diagonals. The next question that is asked is, how many number of body diagonals? Number of body diagonals. Now let's try to understand what is body diagonal. Okay. First, just write it down. This is what is known as edge diagonal. You need to have complete understanding of all these diagonals. Okay. Now let's talk about the body diagonal. So what is a body diagonal? You take one corner and you take the complete opposite corner of that. This whole will be considered as a body diagonal, right? A diagonal that is crossing the whole body is your body diagonal, and it will pass through your body center. So what can I say? I can say that a diagonal from here to here is a body diagonal. So this is the body diagonal. So 2 corners together combine and give you one body diagonal. How many corners do you have? 8. So how many body diagonals do you have? 4. So you have 4 body diagonals present. Okay. The last question that is asked to you is number of face diagonals. Now let's try to understand what is a face diagonal. Okay, now my dear students, how will you understand this? Consider this face. The one point to the opposite point of a face will give you one face diagonal. This particular point to this point will give you another face diagonal. So this is known as face diagonal. Okay, so how many face diagonals do you have? You have 6 faces and each face has 2 diagonals. So can I say that 6 into 2? Total of 12 diagonals are, you have 12 face diagonals. Okay, and my dear students, this particular point out here, this is the face center. Where the 2 diagonals cancel out each other is your face center. And let me tell you, this point, this particular point, my dear students, where all the edge diagonals and body diagonals come and cross each other is your body center. So this is your body center. Okay, this is something which you need to understand about a cube, because all these things will be used in the coming section. Okay, I hope you're clear with this. You need to have a clear understanding of this. Write it down. I'll have some water and then we'll move forward. I hope you've written this. Now let's move forward, my dear students. So now the next topic which we will be discussing is the packing fraction. Okay, so what is packing fraction? You need to understand this first and then we'll move forward. So my dear students, when you talk about packing, so packing means that let's imagine I am in a room. Let's say this is a room and this room's volume is, let's say, 100 meter cube. Okay, and this is me. This is me. Okay, and my volume is, let's say, 10 meter cube. Okay, so how much amount of this room have I occupied? How much have I occupied? I have occupied 10, that is my volume, upon the total volume, which is 100. So 1/10 of the volume I have occupied. So this is the packing fraction of this room. Okay, because only I am standing here. What if this whole room is filled with people and everyone will have some volume, right? Yes, so the packing fraction for that room would be the volume of all the people present in that room divided by the total volume of that room, right? Yes, so this is exactly the packing fraction. What is packing fraction? Packing fraction actually tells you that how much of your room is occupied and how much of your room is vacant. The part which is occupied will give you the packing fraction and the part which is empty will give you the void fraction. These two terms are used again and again: packing fraction or packing efficiency, void fraction or void efficiency. Okay, so now let's read the definition. The fraction of the volume of a unit cell occupied by the atoms is called the packing fraction. Now, if you will talk about the packing fraction of a room, you will say that the volume your atoms have occupied divided by the total volume of the room, right? Yes, so now let's try to find out a formula for the packing fraction. Okay, so now my dear students, for packing fraction, I know that packing fraction will be the volume of total volume of atoms, total volume of atoms divided by the total volume of the room, total volume of room, right? Of unit cell. Now let's try to find out this. Okay, so if you want to find out the total volume of the room, you know that one atom is a sphere. You know that one atom is a sphere, right? So the volume of sphere is given by 4/3 pi r cube. I hope you're clear with this. Yes. Now let's say you have effectively 2 atoms present in the unit cell. So how much volume of the atoms are present? 2 into the volume of one unit cell, because the atoms would be same. Yes, ma'am. So the total volume of atoms will be number of atoms, or I could say effective number of atoms into the volume of one unit, volume of one atom, right? Yes, perfect. Now, what is actually the effective number of atoms? Effective number of atoms present in a unit cell is actually the definition of rank. So can I say that the total volume of the atom would be rank into volume of one sphere atom, that is 4 by 3 pi r cube, right? Yes. So this is the volume of total volume of atoms present in a unit cell. This would be the total volume of the atoms present in a unit cell. Okay, yes. Now let's try to calculate the volume of unit cell. Total volume of unit cell. So the total volume of unit cell is given by, since it is a cube and the edge length of a cube, let's say, is A. So we can say that it is A cube, where A is the edge length of cube. I hope it's clear to you. Yes. Yes. So now let's incorporate all these into the formula. So the packing fraction will be equal to rank. Total volume is rank into 4 by 3 pi r cube divided by my dear students, divided by volume of the cube, that is A cube. So this is actually the formula for the packing fraction of a unit cell. This is how you calculate the packing fraction of a unit cell. Calculate its rank, multiply it by 4 by 3 pi r cube and divide it by A cube, and you will get the packing fraction. Okay. Now, today we'll calculate the packing fraction for a simple cubic unit cell, and then we'll move forward. Okay. Yes. So let's start with the simple primitive unit cell. Let's say you have a primitive unit cell, something like this, okay? And I know that in a primitive unit cell, all the atoms are present at the corners. All the atoms are present at the corners. Now, before starting this, I want to tell you something, my dear students. I want to tell you something, just keep it as a point in your mind. Whenever I have drawn a unit cell, I always tried to make the unit cells like this, right? One is present here, one is present here, as if they both are not touching each other. But in reality, my dear students, so what actually happens is your atoms are present something like this. I'll just make on one edge so you will understand. This complete atom will be touching this atom like this. Okay, this is how actually atoms exist. But if I had drawn like this, I would not have been able to show you how the atoms are present at the corners. If you will see your NCERT, you'll see the correct diagrams where all the unit cells, all the atoms at the corners are actually touching each other. So in reality, they are touching each other. And if they are touching each other, and this is the edge length of your cube, and this is the radius of the unit cells, then your A will be equal to 2R, right? Yes, since they are touching each other. Okay, so this is something you need to keep in mind, that we draw it like this, but in reality, the atoms are touching each other along the edges in a primitive unit cell. Okay. So now, my dear students, I have drawn this, and you know that these both are touching each other in reality, right? Yes. So the actual picture would be, I'll make just one edge. I'll make one edge here. The actual picture would be that your atom, one atom is here and the other atom is here. It is actually touching it. Okay. So this is the real picture. So can I say that the edge length A is actually equal to the sum of these 2R. So A is equal to 2R. This is the relation that I have just found out, and this is very important for me, right? Yes. So now what you are going to do is, my dear students, calculate the packing fraction of this particular unit cell. How are you going to calculate this unit cell's packing fraction? Let's calculate the volume of atoms. The total volume of atoms would be rank into 4 by 3 pi r cube. It is a primitive unit cell. So what will be the rank? Rank will be, ma'am, number of atoms at corners upon 8 plus 0, which is equal to 8 upon 8 plus 0. So this is equal to 1. So the rank of this unit cell, primitive unit cell, is 1. Right? Yes. Since the rank is 1, I can say that packing fraction will be equal to 1 into 4 by 3 pi r cube upon the edge length is a, so a cube. Now I'll be using this equation, which is a is equal to 2r. I'll be using this equation into this. Now let's write that a is actually equal to 2r. Okay, since a is equal to 2r, then packing fraction will be equal to 1 into 4 by 3 pi r cube upon a is equal to 2r whole cube, right? Yes, this will be 4 by 3 pi r cube upon 2 into 2 into, this would be 8r cube. R cube cancelled. 4 by 3 into 8 pi. Right? Yes. So this is 1, this is 2. So this would be pi by 6. Pi by 6 is the packing fraction. Pi by 6 is the packing fraction, or I could say this is approximately equal to 0.52. So the packing fraction for a primitive unit cell is 0.52. This is the packing fraction. And if somebody asks you what is the packing efficiency, the packing fraction, you will come across these words, packing fraction. If it is packing fraction, then this is equal to 0.52 since it is a fraction. Then what would be the void fraction? What is void fraction, my dear students? How much of your space is empty? If 0.52 is packed, then how much is empty? 1 minus 0.52, which is equal to 0.48. So this is your void fraction. You also come across a few names like packing efficiency. If you are ever asked packing efficiency, so what you have to do? Just multiply 0.52 by 100 and 52% will be your packing efficiency. And what would be your void efficiency? This would be 0.48 into 100, which is 48%, nearly. Okay, these are the near values. So you are generally asked such questions, and this is how you use a relation and calculate the packing fraction for a unit cell. I hope you're clear with this. You can pause the video, write it down, and then we'll move forward. You can write here that atoms touch each other, are in contact with each other at the edges. Okay. This is something you need to write so that you will always remember. Please write it down and then we'll move forward. Next is this. Okay, I hope you've written it. Now, let's see what is void fraction if you need a technical definition of void fraction. The fraction of the volume of unit cell unoccupied by the atoms is called the void fraction. Okay, and 1 minus the packing fraction will give you the void fraction. So you can say that your void fraction will always be equal to 1 minus the packing fraction. Okay, I hope it's clear with you. Perfect, my dear students. Let's move forward. Next is coordination number. Now, my dear students, the next other thing which I want to make you explain today is coordination number. What is coordination number? What does coordination number mean? Coordination number means that how many atoms are in direct contact with one particular atom. If you are asked the coordination number of an atom, that means that how many atoms are in direct contact with that particular atom. Let's try to understand this. Let's say you have one-dimensional packing. If you are talking about one-dimensional packing, you will have atoms like this. You will have atom like this. And if I ask you the coordination number of this atom, what will you say? two atoms are in direct contact, so the coordination number will be 2. The coordination number will be 2. Similarly, if I talk about the two-dimensional, if you have two-dimensional packing, then you will have atoms something like this. Let's say you have atoms here. Now, can I ask you the coordination number of this particular atom? You will say how many atoms are direct contact? 1, 2, 3 and 4. So the coordination number is 4. So the number of atoms in direct contact with the atom, it gives you the coordination number. Okay. So it is the number of atoms making contact with the given atom. The coordination number is defined for the given atom, and the atoms making contact are called the nearest neighbor. Also, coordination number is known as the nearest neighbors. Many a times you will not be asked the coordination number. They'll ask you what is the, how many are the nearest neighbors to this atom. So definitely they're asking you the coordination number. Okay. Yes, I hope you're clear with this. Write it down and then I'll make you understand other things as well. Okay. I hope you've paused the video and you have written this. Now let's move forward, my dear students. Now you have to calculate the coordination number. Okay, so the coordination number for a primitive unit cell, the distance between the center of the nearest neighbor. So now we'll be understanding the coordination number for a primitive unit cell. How are you going to understand it? Let's draw a primitive unit cell. You have a primitive unit cell like this. You know that the atoms are present at the corners only. So you have this atom, 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 atom and atom. And you know that along the edges, these atoms are in contact with each other. Okay. So now, how are you going to do this? Okay. You are generally asked the first nearest neighbor. If you are asked coordination number 1 or you are asked the nearest neighbor, you have to find out the minimum distance an atom is present to, and that would be your nearest neighbor. Let's say we want to find out the coordination number for this atom, then we'll see that what is the nearest distance at which an atom is present. Okay, if I see, I can say that this particular distance is A, right? This edge length is A. So an atom is present at A distance from this. The next nearest distance is, if this is A, you know that this is also A, right? Yes. The next nearest neighbor that you can see is, my dear students, this one. Now let's try to calculate what is the distance for this one. Okay. So if I see that it is something like this, this is A distance, this is also A, this is A, this is also A, this is 90 degree, and you need to find out this. Let's say this is A, B and C. So this is A, B and C, and you have to find the value of AC. So how can you find? This is simple maths, my dear students. Pythagoras theorem. You know that AC square will be equal to AB square plus A plus BC square. So AC square would be equal to A square plus A square. So AC square will be equal to 2A square. So AC value would be root 2A. So the length of this particular part is root 2A. So can I say that this atom and this atom are at root 2A distance to each other? Right? Yes. Is A distance closer or root 2A distance closer? Ma'am, A distance is closer, right? So this atom, the atom which is at A distance, will be its nearest neighbor. The first nearest neighbor will be at A distance to this. So you have to find how many atoms are at A distance to this particular atom. Okay. So we can say that the coordination number of primitive unit cell, we don't know, we need to calculate. The distance between the center of the nearest neighbor is A. This we have found out because root 2A was a bigger value, A is a smaller value. So now, my dear students, let's try to find out how many atoms are present. So for this, again, you need this unit cell. Okay. Let's join these two. Now your atom is present here. So if your atom is present here, so my dear students, this particular atom will be at a distance to this particular atom will be at a distance to this particular atom will be at a distance to this. I hope you understand this. You know that a cell would be present at back also, which would be at a distance to this. You will have one more here also, which will be at a distance to this. And you will have a distance to this as well. So total 6 atoms are such which are at a distance to them. So the coordination number would be 6. So the coordination number would be 6. That is 6 atoms are such that they are present at a distance from this particular atom. So the coordination number for a primitive unit cell or the first nearest neighbor is at a distance, and the coordination number is 6. I hope you're clear with this. Perfect, my dear students. You can write this and then we'll move forward. I hope you've written this. Now let's move forward, my dear students. See, the next, now we have discussed the first nearest neighbor. What if somebody asks you, please give the second coordination number of primitive unit cell or the next nearest neighbor? So what does that mean? First nearest neighbor means the nearest distance, which was A. If somebody asks you the next nearest neighbor or second coordination number, that means you have to find out the second nearest distance. And if you see the primitive unit cell, my dear students, the second nearest neighbor is at root 2a distance. The second nearest neighbor is at root 2a distance to this. Okay. So how will you write this? The next closest equidistant atoms are called the next nearest neighbor, and the next nearest neighbor is obtained along the face diagonals at a distance of root 2a, at a distance of root 2a, at a distance of root 2a. This is how you calculate the next nearest neighbor or the second coordination number of this primitive unit cell. And the coordination number or the second coordination number of primitive unit cell is 12. It is 12. Now, the question is how 12 came. I'll give you a trick and you can find all the coordination numbers in single bit, but I'll make you explain how this coordination number 12 came. Okay. Yes, let's see. So we know that the second coordination number will come, I'll use this part only. The second coordination number will come, my dear students, at root 2a distance. So you need to see that how many atoms are present at root 2 distance to this particular atom. Okay, so you can see that this is a root 2 distance, root 2a distance. So one atom will be present here. Obviously one atom will be present here. So 1, 2. Similarly, my dear students, you will have an atom here also. You will have atom backward and face thatward. How many faces are present in connecting to this? 2. Then you will have 3. Then you will have 4. And this is how you will get total 12 faces. You need not understand how they will come. I'll give you a trick and you will find the answer in a bit, my dear students. But for now, you can understand that this is the root 2 distance and this is the root 2a distance, and this will be your second coordination number. This will be your second coordination number. Okay, yes. So now let's try to understand a little. I'll make you understand this. Okay, so how are you going to understand this? Can I just erase this whole part and I'll make you understand this? Okay, now see. Okay, so now you have an atom present here and you want to calculate the root 2a distance atom. You'll have one atom here and you will have one atom here. I hope you understand that this is root 2a distance, root 2a distance. Can you see this face, my dear students? This is also root 2a backward. So you have to imagine this. You have to imagine this face. You have to imagine this face and you have to imagine upper face. So this line and the backward line. Consider a corner. See one face, two face and 3 face. One corner is connected to 3 faces. One corner is connected to 3 faces. Okay. You know that these 3 are the root to a distance parts. Now, imagine here, your imagination will be the biggest role playing part. I am talking about this face, this face. So if I extrapolate this face, you will get something like this, right? Yes. If I extrapolate this face, you have 3 different faces. I am extrapolating those 3 faces, right? This is the one face. Can you say that if you have atom here, you will have atom here, here and here. So total 4 atoms at root to a distance. Similarly, now you extrapolate, my dear students, the backward face, this face, the backward face. Okay, you extrapolate this, you will have like this, like this, like this, and like this. I hope you're clear with this. You will have 4 root 2a in this phase as well. So can I add 4 here? Plus. Now you need which color? Let me take blue color. Now you have this phase. Now extrapolate this phase. This, like this, like this, and like this. And you will have 4 here. So total 12 atoms you will have present at root 2a distances in these 4 different phases. If you're not getting this, you can understand this. You know that one corner has 3 different faces attached, right? Yes. And you just need to extrapolate those in the 4 different parts, and you will get the coordination number equal to 12. If you get this, that is amazing. If you don't get this, don't worry. I'll give you a trick in the next class, and you will be very easily able to find out the coordination number. Okay. I hope you're clear with this. Perfect, my dear students. Please write it down and then we'll move forward. If you want to draw it, you can draw it. This is how we calculate the second coordination number of a primitive unit cell. Okay. Now let's solve a few questions and have a better grip on what we have studied today. The question is, polonium crystallizes in a simple lattice. Polonium crystallizes in a simple lattice. The edge of unit cell is this. So now, my dear students, you are given the edge length as 0.236 mm. You have to give the radius of polonium atom. It is telling you that it crystallizes in simple cubic lattice. Simple cubic lattice means you have primitive arrangement. If you have primitive arrangement, then you know that A is equal to 2R. You know that A is equal to 2R, and you are given A value and you are asked R value. So A is 0.236. This is equal to 2R. So R would be 0.236 divided by 2, which is 0.16 and 0.16 something. Do you have something related to this? The closest answer that I can see right now, just a second. No, you have 0.118. Okay, 0.118, right? Yes. So option C will be your correct answer. I hope you're clear with this. This is how you have to solve this question. Perfect? Yes. Amazing, my dear students. Let's move forward. The next question. What are the number of atoms per unit cell and the number of nearest neighbors in a simple cubic crystal system? Simple cubic crystal system means they are talking about primitive. And in primitive, I know that rank is 1. And what is the coordination number? The first coordination number? 6. We did calculate this right now, right? Yes. So 1,6, option A will be your correct answer, right? Perfect. Let's move forward to the next question. Next question. Fraction of volume occupied by the atom in a primitive unit cell is 0.52. So 0.52, option B is your correct answer. Okay. Perfect, my dear students. Very good. With this, let's end our session today. We have discussed a lot of things today. We actually came across what is packing fraction, what is coordination number. So try to revise these, because in the next class, we'll apply this on the body-centered and face-centered crystal systems. So till then, my dear students, keep studying. We'll meet in the next lecture. You have to study and solve your DPPs and practice a lot. We'll meet in the next session. Thank you so much. Bye bye. Take care.